Welcome to the STEM Shed, your source for your below average tutoring needs. So today I'm going to be going over the science of air conditioning, and as we discuss thermodynamics. Now, an issue with thermodynamics is it involves a lot of concepts at once. You're taught about the thermal engine and mostly the Carnot cycle. The Carnot cycle is based on theoretical engine. It involves taking pieces of sand, removing the sand, putting the sand back on a piston. There's hot-cold reservoirs, and you remove, and you add back together, and you insulate it with a perfect insulator. Yikes, that is a lot to understand. So I wanted to work with something a little bit more tangible, something you have everyday experience with. Air conditioning, unless you're in California or somewhere cold that doesn't necessarily use air conditioning. But you generally get the concept. Now, modern AC is more complex than what I'm about to show you, but the principles remain the same. So, the modern AC, the cooling part at least, is a refrigerator. Same as a refrigerator in your house. AC can also involve heating. But anyways, the fridge and AC run off of the Brayton Cycle, which I know sounds like a cool Generation Z hipster millennial name they would give a kid, but it's Brayton. Probably, I'm sure, after some physicist. And but more importantly, the refrigerator one is called the reverse Brayton heat engine. So, in thermodynamics, we introduce you a few ways to represent this process. For scientists, you generally use the PV diagram, and the PV diagram consists of three parts: pressure, volume, and an isotherm, right here. Isotherm is represented, if you remember your algebra, f of x is equal to 1 over x. Alright, so you make a hyperbola. Now you don't have the hyperbola down here because, again, this is all down here is in another universe. We're in this universe, so we can't go negative, because if we went to 0, 0, 0 pressure times 0 temperature, zero pressure to 0 volume, you'd be at absolute 0. So going below it would mean you went to another universe. Alright, so what this shows here, and this is right here I have, is written as eternal energy. I'll go on that later on. But one of the big important, and sometimes it's written as delta E. This is a state function, so it doesn't matter how. You got there. All that matters is you're there. So it doesn't matter if you start from here to there. So work is equal to force times distance, right? Well, remember, pressure is a force, and a change of volume involves a change in the distance. So you have a three-dimensional cylinder right here, and it moves up. Well, guess what? A distance has changed. So the three things you have to know. So, and also, I'll note here, this work does not equal pressure times change of volume when it comes to thermodynamics, except for one case. But it does not equal this. You have to do the integral, because this V equals the infinitesimal, or infinite amount of changes of volume. It's infinitesimally small. Alright, so you can't go from one to the other, because if you just went bam, bam, so much stuff would happen there. It would be a combustion, which is how diesel engines work a lot. Just a slamming and compression. It's just something that doesn't generally work. So, but in this case here, you have isobaric. I'm not going to do the integration. I'm going to go through the, I'll do the integration in another one. This one, I'm just going to go through what the formula is. So isobaric is negative pressure times change of volume. And this is the only one that does that. Now it's negative because it's work being done by the system, which means it's negative. It's just how they chose it. They chose a different way, which I'll explain in another video. It could be different. It can be positive. In this case, it's negative. Work was done to it. And what it is, it's a volume change. That's all it is. The only thing, the pressure stays the same. The only thing that changes is this. So, for example, from here to here, I'm giving this a direction. This is isobaric. Next one, adiabatic. Oh, and we'll be using this one in the refrigeration. Next one up is adiabatic. So adiabatic, diabatic comes from Greek. Diabatic is basically Greek for passable. But it says A right here, so it's not passable. So this one here, again, I'm not going to derive it. I'm just going to tell you what it is. So you got N, number of moles. I don't like this one. N is the number of moles. I got a better one. N, the number of moles, times the heat capacity at constant volume. Alright? Now I'm going to go over this real fast. You're confused. You're like, what do you mean the volume changed? No. The volume of the cylinder changed, but the volume of the molecules is the same. The heat capacity is the same. The volume is staying the same. All the molecules are there. I believe that's my understanding of it. Because what is changing in this one is going to be the temperature, delta T. And this right here is an important process to know, delta T. Alright? Remember, I'm doing work right here. So this is actually, and this is equal to Q. That's it. It's equal to the heat output. So it goes, heat goes in, heat goes out. It's one of those two. And for example, that one, this one's a little bit more hard, a little bit harder to draw, but let's start right here. And it goes down something like this. It's not quite an isotherm, and the reason why is because there's basically, you have almost in a sense an extra component right here. They usually use gamma right here, so this gamma will drop this faster because it will make this a lot larger, a lot faster, depending on where you're at. So that's that. So you get isothermic. Isothermic, that one's, so the temperature is going to stay the same. Your temperature is constant. Your work is negative, so you got negative work. So in fact, this might be a negative. I'll have to double check this one, but this is going to equal to N. Remember the ideal gas law, PV equals nRT. So in this case here, you just got N, R. This is the gas constant, T. All right, the temperature is the same, so the temperature is not going to change. And then it's going to be the natural log, and this is from we integrate over 1 over V. So you got natural log of V2 over V1, and this will equal your work here. So got that one, and the last one, oh yeah, and that one's kind of simple. You just go, basically just going to follow this. All right, so your volume is going to increase while your pressure decreases if you're going this way. And right now I'm working on this direction for all of them. All right, so we're going this direction, this direction. Last but not least, isochoric. Choric comes from the Greek for chora, which means space. So same space, isochoric. All right, so if you look at this formula here, we'll go to this one. All right, so we got, in fact, let me just go and draw this part first. So I'm going to start right here. I'm going to go right here. All right, have I changed volume? No, I haven't. So the volume, and I'm going to go ahead and do this, doesn't matter the pressure. Pressure could be 1 billion minus pressure times the change in volume. Well, V, we'll say V final is equal to V, or minus V initial is equal to negative pressure times 0. And that is equal to 0. Now, this is interesting because what this means is that somehow the temperature changed. But to do this process, it involves a lot more work, and I'll do that here in a second. All right, I'll go back to that one here shortly. So another diagram I want to go to is what's called the scientists and engineers will use this a lot. And that one is called energy transfer diagram. So this is this right here. So what you have here is a hot reservoir and a cool reservoir. Now, if you know from the second law of thermodynamics, heat can only flow to cool. It can only go down. So in this case here, but in this case, this refrigeration, heat is going up, or cool is going up. Again, it's going up. And it's going into this hot reservoir. Now, a reservoir is a theoretical concept where usually you assume it's infinite amount of stuff. It's infinite amount of heat. Not 1,000,000 degrees, it might just be 100 degrees, but forever. So no matter what you put in here, it will not change. Any change you put in here is so insignificant, it will not affect this. And it's the same reason why if you build a fire, it doesn't, even though you might be hot 5 feet from the fire, it does not get hot in China. Unless you're in China, it doesn't get hot in America. So this is this. And the thing, but the reason they can do this is because of this work. And they'll draw this here as a system. This would be the refrigerator itself. So work goes in, electricity to run the compressor and all the gadgets goes into the system, and it pushes the cold up here. That's the only way this can happen. So that is that system right there. Now this diagram, I don't like those diagrams. They've been very confusing to me. Now the Brayton cycle uses adiabatic. Adiabatic and isobaric changes. So same pressure and then not passable. Now a lot of things you need to question. Says, okay, well, why not isothermic? Okay, you're trying to cool the house down, right? Why would you want the same temperature? So for this one here, you just got to say, okay, well, this one's obviously not it because I don't want to be the same temperature. I'm not going to put a bunch of work in to get to the same temperature. So, okay. And what about isochoric? And remember, choric means same space, so volume changes. Okay, I don't see any real reason why not. Does it do anything? I mean, it says it does no work. So work is, has no work. So, no work. So that sounds great. I'd love to not do work and change the temperature, except the problem is, because if you want to drop the temperature, this Q needs to drop. This needs to go down. This needs to leave. And something needs to happen to it. It needs to be a negative Q. It needs to go away. All right? But the work here is 0. So the only way you can do this, and when I say work is 0, I mean work by the system. This can't do anything. This can. This can. This infinite reservoir of cold ice can do work. The pressure of the exterior can do work. It's just this can't do work. So what I have here is a piston, and if this pressure was 0, this piston would shoot up into space. If it was a vacuum, it would shoot up. Doesn't matter how cold you made this. It's going to, unless you made it to absolute 0, this will move itself up. So it doesn't matter how cold this is. But what you can do is, if you have them in equilibrium right here, you can put these 2 pins in each other, and then it doesn't matter what you do. You could put the pressure of the sun on here, or put the vacuum of space. It does not matter. It is not going to move this thing. Alright? So, again, that's why you can only move temperature. Well, the only thing it can do, there's no work that can be done. This cannot change volume. Remember, volume is the only thing that changes. It can't change volume. What can it do? It can lose heat or gain heat, but either way. So in our case, we want to lose heat. So what we want to happen is all these molecules, we want them to lose energy. So we want Q to go into here. That's your isochoric. So it's something, it's not really feasible. You can't do it. So it's not going to be an option. So we are now left with 2 paths. So we know it's isobaric or adiabatic. It's going to be one of those 2. In fact, it's both. So this is the Braketon cycle. This is what it looks like. So this is the work right here. Now, it's kind of easy to tell which one's the isobaric because same pressure, right? The volume only changes. So you go from here to here. All right? And then you're going to go down this. It looks kind of like an isotherm, but it's not. You have that extra component in your f of x, shouldn't do in blue, but is equal to 1 over, it's like x to the, say, squared. Makes it a little bit different, right? So that's this right here. So it's same pressure. And it does this. So, and you can see these are your isotherms. So at this one right here, this crosses some kind of line. In fact, we're going reverse. So your colder temperature is up here while your hotter temperature is down here. So you're actually going to be going in this direction for refrigeration. Going this way and that way. Alright, and I'll explain that in another video, make a little bit more detail, but as you can see, it goes from a hotter temperature to a cooler temperature during this process right here. And then up here, it goes from a hotter temperature to a cooler temperature right there. And then it crosses, and you cross this line right here. So there's a lot of cool work that goes on in it. And please tune in to some of my other videos that I should hopefully be getting done this week. I'm going to be taking apart a portable air conditioning unit. I'm going to go look at my air conditioning unit. And then I'm going to do a full detail about what is going on in the air conditioning unit.